Hello and welcome to another SkyCiv tutorial. Today we're going to be covering the topic of designing and optimizing your structural elements using S3D and Beam, and we're going to be focusing on using the Designer module, which allows us to test all the different sections within a particular library to find the most optimal design or the most optimal section for our design. So we're going to look at we're going to look at two cases. So one is a structural 3D model with some still elements, and I'll show you how you can select a particular library in order to test all the different cases in or the different sections in that library. So we want to just sort of review the model in 3D. We've got some I-beams here at the top and some hollow rectangular sections as well as the columns. So we can also add a third section. Let's add some equal angles, and I'll show you how this translates to the designer. So if I go section builder, and when I'm selecting a library, I'm selecting it with the mindset that, for instance, if I choose equal angles, I'm going to test all these different sections when I go to the designer. So it automatically picks up what section library we've loaded, and then it's going to test all those sections. So it doesn't matter too much which I start with, so I can start with, say, a 45 by 5 equal angle. All this means is that we're going to test all the different sections in this library, but if it comes up with an optimal result, we'll just skip the rest. I do recommend selecting something that you think will work just by default, because if it does work in the beginning, then it can focus on optimizing and finding the best result. If it does fail in the beginning, it'll still work, but it will just be sort of increasing the material usage to get you to a passing result. So I'm just going to set these members as being section ID 3. So now we can see we've got 3 sections, again reviewing it in the model in the 3D renderer. So these are quite thin. We'll see how these interact once the design check is run, whether they pass or fail, but they probably will fail, and we'll show you how that results or how that changes the optimizer. Okay, so another thing we can do is just before we run it, let's just have a quick look at the center of gravity, which will tell us the overall weight for this structure, which is about 8,100 kilos. So we're going to see how, after we run it, the designer, how much we reduce the material in the structure by, whether we can see some considerable savings there. This is a good way to just check briefly where we're at for the structure mass before we go and run the designer. Another thing you can use is the bill of materials. So this will just give you the overall weight usage or cost usage. If you've got some cost information, you can put in some values of how much each of the sections cost per unit. So you can get some pretty in-depth understanding of the cost savings to the client. But for now, we're looking at about 8,100 kilograms, and we'll see how much the optimizer can reduce that by. So when we're doing this sort of design, we can just run through our kind of standard procedure of running an analysis. You can add load combinations, different loads, all that will be considered in the designer. And then we're just going to start a design code. So the optimizer or the designer will work on pretty much every design standard, including cold form and timber. For today, let's do a Eurocode test. So we've got a metric model, and we've loaded sections from the Australian library, so you can kind of cross-match a few of the different elements, but we're going to predominantly look at the Eurocode for this test. And one thing I do like to do is just start by running a check. So just let's get an idea of what the structure is doing from the beginning. So we can see we have some failed I-beams here at the top, and it also looks like our bracing, our angled members, are failing by about a factor of 3, so 2.8. So those utility ratios, we want to hopefully have something at the end that is producing all green passed results. So we want to be designing the I-beams, the angles, and then we can also look at the columns, which is these RHS. And we can see they're only about 23% utilized. So we want to we've got wiggle room there where we can improve the design by reducing the material usage or the amount of material in the section, and increasing that utility to somewhere closer to 1. So we've got some kind of wiggle room, we've got some space to optimize for these columns. So we probably want to optimize all 3 sections. So the UBs, which are failing here at the top just by a little bit, but they're still failing. The angles sections, which are failing by quite a lot, and then the columns, which we have, they're passing, but there's quite a lot of efficiency we can gain out of these sections. So now I'm going to start looking at the settings with the designer. So there's quite a few settings. We have variables where you can select what type of sections or what sort of some filters for the sections. So say you have a section height maximum or a minimum, you can control the section height or width parameters. So that might be like architectural requirements or some sort of minimum depth that you need for the design. So you can use those settings for that. Section exclusion list is basically any sections you want to exclude from the designer, because the designer is going to run through every section in this catalog, the UB, or the different catalogs that we've loaded into the model. It's going to go through all of them, but maybe you don't want to use a 200 UB, so what you can do is put 200 space UB, and it will skip any section that has this in the name. So you can comma separate them, so say you don't want to do any 200 UBs or 180 UBs, it'll skip those because they have 200 UB in the name. On the flip side, if you only want to test a particular library or type of section, you can just put in an inclusion list. So say we only want to test 180 UBs, we can put that in and it will only test those section names that have 180 UB in them. So you can control kind of what section you're able to use or what sections you don't have available to you, you can put in here to skip those. You can also control the max utility ratio. So as we're running the designer, we're going to aim to try to get as close to this number without going over it. So a typical one value would be 1. We want to design right up to the utility ratio of 1, but I'm just going to leave it as 0.95, and we can see what kind of results we get and whether they meet those criteria or not. Then we have on the right side the member settings. So we can control which sections we want to optimize. So we want to optimize all 3. We've kind of reviewed the design and seen all 3 have some sort of design like optimization required. So you can load all 3, or conversely, if you just want to do 1, you can just have 1 in there and just focus on designing 1 section at a time. And then finally we have our analysis interval. And what this is how often we want to run the analysis or the FEA in between checking the different sections. So having a 1 would mean that after we change a section and test it, we then want to run another analysis to update the internal forces and the deflections before we run and test another section. So there's a bit of a trade-off here. If you reduce this number to 1, it's going to run an analysis between every single section that we're testing. So it's going to take a little bit longer because we have to re-perform the FEA. Otherwise, if we increase it to say 5, we can have a happy medium where we're only rerunning the FEA every 5 sections. And the sections are ordered within by area, so they are somewhat relatable. So you can do something like this where you're only running the FEA every 5 sections and still get some pretty good results because the deflections are still updating by the area. The other option you can do is just turn this off completely. So by setting it to 0, it won't run the analysis in between any sections. So the results, the internal forces that we ran, that we received from running the analysis, is the results we will use for every single section. So we're going to test every single section in the catalog with the same internal forces. So having it to 0 is usually a good place to start. You can usually get some pretty good results, but you might see them not matching the final design because you'll need to rerun the analysis to get the updated forces. So for now, let's start with just an analysis interval of 0. So this will be the fastest to run because we're not re-performing the analysis in between every section. So then, yep, once I've committed the settings, and I hit Designer, it's now going to start optimizing for me. So you can see it's designing all the different sections, all the different UBs in the catalog. It's ordered them by area, and you can see at that point it will skip the remaining ones because it's already found an optimal design. And we can see a lot of this in the log, which we'll review once these results come through. It explains a lot of what the designer is doing to kind of have that open transparency to the engineer to be able to review what the designer is actually doing. So you can see now it's moved on to the second section, which was the RHS, these columns. It's testing all the different sections in that catalog as well. And yeah, not running analysis in between, so we're just using the same internal forces that we originally had when we performed the solve or the FEA. So the only real result that typically has a large effect on is the deflection limit. So if you can imagine, you load really heavy sections to begin with, the deflection limit might fail, and if you have the interval set to 0, no matter what section you use, it's always going to fail that criteria. So that's kind of why it is important to select something that you think is more or less close to something you would choose initially. Then you're going to get more accurate deflection results being used within the designer. So you can see it's almost complete. It's just designing the final equal angles, which was used for our bracing members. And we should have some results coming through soon. So there they are. You can hit view results. And now we can kind of review what the designer has done. So we've gotten from 200 UB 22.3. We've increased the size a little bit because it was failing. It was about 1.03 or something like that, I think. Whereas now we have it under that criteria of 0.95. We can also review the iterations. So what were the different tests that the designer ran to get to this result? And we can see this is the original, so it was 1.1 that was failing by. And we've tested a few other sections and found our way to this optimal design of a 200 UB 25.4, which is 0.949, which is just under that 0.95 criteria that we set in the settings. So pretty happy with that. If you did want to select a different section, you can select a different section. So if you did have, you wanted to sort of leave a little bit more wiggle room and keep it under 0.9, you can do that. But for now, we're going to load the suggested 200 UB 25.4. So having a look at our columns have reduced by quite a lot. We've gone from a 350 by 250 to a 250 by 150. So again, we can review the iterations. We can also sort these by cross area or utility ratio. So we can see we were sort of using 4,500 millimeters squared, we were using 11,000 millimeters squared. Now it's about 4,500. So we've more than halved the section size in terms of cross area and weight. And in doing that, we've gotten a result of 0.89 or so for a utility ratio. So pretty happy with those results. And then we can finally review the equal angle. So this one was failing by a factor of 3. So we can see originally failing by 2.89. And then now we have a equal angle that passes the criteria. So 0.83. And it's a 150 by 10 equal angle. So pretty happy with all those 3 results. I'm going to go ahead and commit those changes. And so what this is going to do is load in those optimal sections into my model, and then also re-perform an analysis and a design check, just to make sure what we're looking at is close to what we had during the designer. And this is a good scenario because it shows that having the interval off, set to 0, means that the deflection, once we update the internal forces, it is now failing some of those design criterias. So what we can do is, it looks like the columns are working and the equal angles are all good, but more so on the UBs, and that's because we had the interval set to 0. So what we can do now is just set that to 1, and we just need to optimize or redesign this 200 UB. So what this is now going to do is re-perform the optimizer, but we're going to be rerunning the analysis in between every section that we use to then get the updated deflection forces. So I could have done this from the beginning. I could have just set the analysis interval to 1 and done all 3 sections at the same time. It might take a few minutes, so you might want to set it and then go grab a coffee and come back to your results finished within as it might take a few minutes. But this is just an alternative way to work, and also just wanted to demonstrate the difference between setting analysis interval to 0 as opposed to setting it to 1. So yeah, 2 types of ways that you can design, whether it's just a sort of a trade-off in terms of whether you want to turn the analysis interval off completely, and or which will run faster, or increase the intervals, and it'll just take longer to run. But we can see now it's gone for a heavier section, so 250 UB 25.7, and we've got a utility ratio of 0.89. Another useful thing is we can view the log, so we can have a look at now how that was running the designer. So we had 28 sections in the library that we loaded, and we can see now we tested the 150, we reran the analysis results, and then we did a design check, and you can see the different utility ratios and areas, so you can kind of see how they're converging and coming down to where we have a sort of design that's passing the criteria. And you can see that we're rerunning the analysis every single time we do a section check. And then it gets to a certain point where any other sections are kind of redundant results. We've already found an optimal design. We've run a couple more just to be safe, but we can skip the remaining sections in the library because they're just going to yield redundant results, and we've already found our optimal section. You also get some sort of statistics or some final summary values. So we've got the original section, which had a 1.01, and now we have a different section, the 250 by 25, showing 0.89 utility, and we've increased the material usage, which makes sense. We've gone from a failed design to a passing design, so we've increased the material usage of this section by about 1.2%, which is fine because now we have a passing design. So once again, I will just commit those changes. Rerun the analysis. And rerun the design check to just confirm that that is all now passing, which we can see now. So we can review the UBs, and we can see that they're all passing. One of the members doesn't have any internal forces, so that's yielding a 0. But we can see that the remainder of the sections, particularly those ones that were failing, are now all passing the design requirements. And just to see the sort of overall performance of what we've just done, just optimizing this structure, we can just go back to our center of gravity calculation, and we can see now that's 6400. So down from, it was 8150 to 6400, which is a pretty considerable saving in material and CO2 emissions from using steel. So that's how we can optimize using the designer in structural 3D. Next, we're going to have a look at a simpler version. So we're just going to have a look at SkyCiv Beam and how we can do the same procedure with a simpler model just for a single element. It could be in our own structure, or it could be a completely different design. So here I've got a somewhat complex 2D element. I've got some fixed supports on either end, roller support, and I also have a hinge joint as well. And very similar to what we did in S3D, we're just going to launch the section builder, and we can choose from any of our libraries. Let's go for a Canadian section. We can do maybe another HSS, square HSS. So whatever we choose here is this library that we're going to design for, and submit that. And so now we're going to proceed with solving. So it's a very similar process to when we were doing the design for S3D. So we're just going to go through and run an analysis. and perform a design check. Let's just see where we're at, whether the member is passing or failing. So we can see we've got a utility of around 1.5, so it is failing, and we have some moment forces it's failing on, some deflection, some combined design checks that it's failing, but overall looks about 1.5 the ratio. So we can just click optimize here. Very similar settings, it's all built on the same tech, but this time maybe we want to try to design right up to a utility ratio of 1. And in SkyCiv Beam, because it's a single element, you can be a little bit more flexible with the analysis interval. I usually set it to 1. It's not going to take too much longer to rerun an analysis on a single element, so I'm happy running that as 1. We can just click optimize section. So now we're going to rerun the analysis between every section, and we're testing all the sections in that Canadian library. And sometimes this note comes up, but it's just if you want to reset, but you can ignore that one. So it's able to find an optimal design at HS 178 by 178. We can view all the runs, so we can see, okay, well, which was the lightest section that it tested, and it looks like this was our most optimal design. So anything below here was obviously failing the design criteria of 1, but then it was able to find a design that met the criteria that had the lightest cross-section area. So you can see that has found a pretty good result. Pretty happy with that design or that section. So I can just select that section and then just commit the optimized section. And that's going to do the same thing. It's going to rerun the analysis, so we can perform the design check again, just to confirm that the result is all in sync and that we can move forward with this design. Great, so we have that result that was matching 0.88, and we've gone from a failing cross-section at 1.5 to now being an optimal design from that library. So we hope this tutorial helps you design more efficiently using both S3D and SkyCiv Beam combined with the designer or the optimizer module. If you have any questions, feel free to drop them in the comments below. Otherwise, we hope you continue to enjoy the platform. Thanks.